We're going to start by looking at inductive reasoning. So inductive reasoning is when you look at specific examples and then use those specific examples to draw a conclusion about the broader picture. So whenever you draw a conclusion using this inductive reasoning, you're creating a conjecture or a theory because it's just an assumption that's based on the collected evidence. So you can think about inductive reasoning as that process of reaching a general conclusion by examining specific examples. So I want you to take a look at these examples. Each of these has a list of numbers that you want to then predict the next number in the following sequences. So if you look at A, we have 3, 6, 9, 12, 15. And inductive reasoning would tell you that if the previous pattern is holding, then the next value in the sequence should follow that same pattern. And so if you thought that the next number would be 18, you would be correct because we're adding 3 each time. Now on the next value, we have 1, 3, 6, 10, and 15. So this one might be a little bit harder to see what's going on. But if you look, you'll notice that to get from 1 to 3, you have to add 2. To go from 3 to 6, you have to add 3. From 6 to 10, that's adding 4. 10 to 15, that's adding 5. And so based on the pattern that you are seeing, then the next value should be obtained by adding 6, which would be 21. And then the last one, 1, 2, 4, 8, 16, how are those values going from one to the other? And in this case, we appear to be multiplying by 2 to get from one number to the next. And so our next value in the sequence should be 32. But all of these are examples of inductive reasoning because we're using the pattern from previous specific examples to draw a conclusion for what's going to happen next. Another example of using inductive reasoning would be looking at a table of data. So here we're looking at the velocity of a tsunami in feet per second and the height of those tsunamis in feet. Our question is, could we determine the height based on the velocity? And so our questions here would be, what happens to the height of the tsunami when the velocity is doubled? So if we take a look at some examples in here where we have the doubling of the velocity, we have 6 and 12. So when the velocity is 6, we have a height of 4. When we double that, we get 12, and we see a height of 16. So right now, I don't know if that is increasing by 12 feet or if that's increasing by 4 times as tall. So let me see if I can find some additional values. Here, when the velocity is 9, I have 9. When the velocity is 18, I get 36. So here, I'm seeing that it's increasing by multiplying by 4, which is exactly like one of the things that I thought could be happening when I went from 6 to 12. Let's just look for one more specific example to make this inductive reasoning conclusion stronger. So if I look at 12 and 24, my height is 16, then my height is 64, which again is multiplying by 4. So now I have 3 specific examples that all hold the same pattern. And so inductively, I can assume that the rule here is that when you double the velocity, you quadruple or multiply by 4 the height. And so we could then use our conclusion to do part B. What should the height of the tsunami be if the velocity is 30 feet per second? Well, I do know that 15 is 25 feet tall. And since my pattern says that it's going to be quadrupled, then I take that 25, I multiply by 4, and I would predict the height to be 100. The challenge with inductive reasoning, though, is that it doesn't necessarily have to continue in the same pattern. And so we're always looking for what's called a counterexample when we're doing inductive reasoning, because a counterexample is going to be some example that disproves whatever conjecture that you've made. The problem with inductive reasoning is it's not an absolute truth. And so as soon as you find a counterexample, whatever conjecture or theory that you've made, you then have to abandon. So in this example, we can look at 3 examples and try to find those counterexamples for these statements. So letter A, my sisters are mammals, my dog is a mammal, my cat is a mammal, the horse in the field is a mammal. By inductive reasoning, all animals are mammals. This becomes an inductive reasoning problem because we're listing a bunch of specific examples of mammals. Every mammal that this person identified were all animals. But the challenge is saying that all animals are mammals is an incorrect conclusion because things like fish or alligators or snakes, those are all animals, but they are not mammals. And so a counterexample here would be any of the animals that are not mammals. Now let's look at letter B. We know that 12 is divisible by 4, 20 is divisible by 4, 36 is divisible by 4. All of those are even numbers, so our conjecture might be that all even numbers are divisible by 4. However, if you look at 6, which is an even number, but 6 is not divisible by 4, so that would be a good counterexample to disprove this conjecture. Now looking at C, we have 2 squared is greater than 2, 3 squared is greater than 3, 4 squared is greater than 4, and 5 squared is greater than 5. All of those are true. Inductive reasoning would have us believe that the square of any number is greater than the number. But there's a few examples that we can think of where this does not work. 1, for example, if you have 1 squared, you're left with 1, and 1 is not greater than 1. It is greater than or equal to, but that's not the conjecture that we came up with. And so that would be an example of a counterexample for that particular conjecture. And then the final one here is that all roads lead to Rome. And you don't have to go very far for you to find a road in your neighborhood that does not lead to Rome. And so that would be an example of a counterexample.